So that wraps up our discussion of insulation, which was one of the three major factors controlling climate. The next major factor is albedo. So, whereas insolation pertains to the level of solar energy entering the system of the Earth, albedo pertains to how much of that solar energy exits by reflecting back out into space. Albedo is the level of reflectivity of a surface. The higher the albedo, the more energy is reflected. And albedo varies based on the characteristics of a surface. For example, dark soil reflects very little solar energy and instead absorbs a lot of it, whereas lighter colored surfaces, especially ice and snow, reflect lots of solar energy and absorb very little. So the soil has a lower albedo or a lower reflectivity, while the snow has a higher albedo or a higher reflectivity. This is what this is what this illustration on the right is representing. The fact that solar energy comes in and hits different surfaces, and depending on the reflectivity of that surface, some amount will be bounced back and escape back into our space. And obviously, if that energy is being reflected back out into space, then it's not being used to heat the Earth. Albedo is measured on a scale from 0 to 1, where 0 represents a surface that absorbs 100% of the solar energy and reflects none of it, and 1 is the surface that absorbs 0% of the light and reflects all of it. Every material can be characterized with a decimal number somewhere between 0 and 1 on the scale. And some common surfaces are represented in this table. So fresh asphalt, which is very dark, is 0.04. Coniferous forest, which is like a pine tree forest, ranges from 0.08 to 0.15. Bare soil is 0.17. Grass is 0.25. Sand is 0.40. Fresh snow is a whopping zero point 0.8. And so, naturally, if different surfaces reflect different amounts of sunlight, different parts of the earth reflect different angles, different reflect different degrees of sunlight based on the terrain that you find there, whether it's sandy desert, dense forest, or polar sheet ice. Different parts of the earth have a different albedo and different capacity to bounce sunlight energy back out into space. And albedo of different parts of the earth changes over the seasons as well. Here you can see a time lapse of satellite imagery of the Earth over the year and how the terrain changes with the seasons. During the winter, there is a whole lot more snow and sea ice than during the summer. And these are some of the most reflective natural surfaces with the highest albedo. Of course, most of the surface of the Earth isn't covered with terrain at all, but rather ocean. And the ocean has an albedo capacity as well. But when it comes to bodies of water, the albedo varies significantly based on the angle of the sun. The more direct the sun's angle, the more energy is absorbed and the less reflected. This graph here shows the relationship between reflectivity or albedo on the vertical y-axis and the angle of the sun on the horizontal x-axis. And as you can see, if the angle of the sun is 0, then almost no energy is reflected. It's all absorbed. But if we follow the lines to the right as we get to um, increasingly dramatic angles, more and more of the energy is reflected rather than absorbed. So this means that the oceans at polar latitudes absorb much less sunlight energy because the light strikes those polar regions at more of an angle compared to equatorial regions. Another thing to draw your attention to is the fact that the two states of water that you see in this list, liquid water in the form of open ocean and solid water in the form of ocean ice, have very different albedo levels. In its solid form of ice, water has a much higher reflectivity than in its liquid form. And so ice actually pushes more energy out of the Earth's system by reflecting it. Compared to liquid water, this is significant because it embodies what we call a positive feedback loop. A positive feedback loop is a cycle that occurs in nature where the result of an occurrence amplifies the original cause. In the case of water, ice, and the albedo effect, the positive feedback loop goes like this. When the Earth's climate becomes cooler, the lower temperature causes more snow and sea ice to be produced. Consequently, the Earth has a higher average albedo because more of the surface of the Earth is ice instead of water, and therefore more solar energy gets reflected back out into space. And because of this, more energy is lost from the Earth's system, and the climate gets even cooler, and the cycle continues. This is known as a positive feedback loop and is thought to have been the driving factor in a historical geological state of the Earth known as the snowball Earth. The snowball Earth hypothesis proposes that during at least one geological period in Earth's history, the surface of the Earth was virtually entirely covered in snow and ice. The most likely period when this occurred was 650 million years ago, because the geological record during this period shows evidence of there being glaciers at the equatorial regions of the Earth. And the emergence of the snowball Earth would have been brought about by a runaway positive feedback loop of a cooler climate leading to a higher albedo, leading to a cooler climate, leading to a higher albedo, and so on until the whole Earth was ice and snow. Obviously, today, the whole Earth is not ice and snow, thankfully. So, how did the planet break out of this runaway positive feedback loop? Well, the leading thought is that volcanic activity emitted large amounts of carbon dioxide and methane into the atmosphere. As did the metabolism of microscopic organisms. This was before multicellular life evolved on Earth. And these higher levels of carbon dioxide and methane caused the climate on Earth to warm. Why would CO2 and methane cause the climate to warm? We'll talk about that in just a moment when we get into the greenhouse effect. But the impact of a warming climate would be that the snow and sea ice would start melting, which would then lower the albedo of the Earth because there would be more open ocean and less ice. And this means that less solar energy would be reflected back into space, and more of it would remain part of the Earth system. And this would lead to the further warming of the climate, which would melt even more snow and ice, and so on. So the positive feedback loop works in the warming direction as well as in the cooling direction. And in fact, getting into a positive feedback loop in the warming direction is one thing that climatologists are very worried about when it comes to the current trends in the warming of the planet that we are seeing. But we'll talk more about that later. On the topic of albedo, there's just one more small detail we need to mention. We've been talking about the albedo of solid surfaces on the Earth, but clouds also play a role in the Earth's albedo. Clouds have a relatively high albedo that rivals the reflectivity of sea ice. Across the globe, clouds actually reflect about 25% of the incoming sunlight before it even hits the surface of the Earth. This, of course, varies depending on the characteristics of the cloud, including cloud type, thickness of the cloud, and the angle of the sunlight. For example, cirrus clouds, which are made of ice crystals, have a higher albedo than cumulus clouds, which are made of water droplets. So we've talked about insolation and we've talked about albedo. There's one more major factor that controls climate, and we can see the importance of that third and final factor if we look at a comparison between the Earth and the Moon. When we are comparing the Earth and the Moon, Earth and Mars, we saw that the average temperature on Earth is 15 degrees Celsius. The average temperature on the Moon is negative 23 degrees Celsius. Given that the Earth and the Moon are so close together, on an astronomical scale at least, they both get about the same amount of insolation from the sun. So you might expect that the reason why the Earth has a higher temperature than the moon is because it has a lower albedo. Maybe the moon is reflecting away more of that sunlight energy than the Earth, so that's why it has a lower temperature. However, that's not the case. The Earth actually has a higher albedo than the moon. They're getting the same amount of insolation, and the Earth is reflecting away more of it. But still, the Earth has a higher average temperature. So clearly, it's not all about insolation and albedo. There has to be something else going on here. And that something else is the gases in the Earth's atmosphere. The Earth's atmosphere contains gases that trap and absorb solar energy. Conversely, the moon lacks an atmosphere, so it lacks the ability to trap energy via this mechanism. The mechanism itself is called the greenhouse effect. The greenhouse effect is the phenomenon where heat that is given off by the Earth is trapped by specific gases with heat absorbing capacity in the atmosphere. We looked at this phenomenon briefly before. Insolation of the sun comes in, it warms the planet, and then some of that heat radiates out. And while a portion of it will escape into space, another portion of it will be absorbed by atmospheric gases and trapped, which causes the Earth to heat up in more or less the same mechanism that takes place in a greenhouse that is used to grow plants, which is why this is called the greenhouse effect. So, how do greenhouse gases perform this trapping function? Because one question that might occur to you is, why do greenhouse gases trap the heat energy that's on its way out rather than the sunlight energy that is on its way in? To answer this question, we need to briefly learn something about the energy spectrum. All light and energy travels in the form of waves. You can see a wave illustrated at the top of this figure. The wavelength of the energy, meaning how frequently the wave goes up and down, determines how much energy is contained within that wave. So, a wave that has more erratic, frequent up and down patterns, like you see on the left, has more energy compared to a wave that has a more gentle and frequent up and down pattern, like you see on the right. We classify energy into different types based on the wavelength and how much energy it has. So, different types of energy you see on this spectrum include gamma rays, X rays, ultraviolet light, visible light, which is the type that we can actually see. All the others are invisible to our eyes, infrared, and radio waves. The reason why greenhouse gases have a heat trapping effect is because they can absorb certain wavelengths of light, but not others. This figure here shows you two things. It shows downgoing solar radiation, meaning energy coming into Earth's system from the sun, and where it lies on the energy spectrum. As you can see, solar radiation is mostly in the visible light region of the spectrum, but also contains some UV and some infrared. The total area under the curve shows the total downgoing solar radiation. And that area that is filled in with dark red shows the amount of energy that successfully passes through the atmosphere on its way down to the Earth's surface. As you can see, the curve is almost entirely filled in with red. And this is showing us that most of the energy received by the sun is transmitted through the atmosphere. It does not get absorbed there. As you can see, the part that's not filled in with red is mostly in the UV spectrum, and we previously discussed about the role that ozone plays in absorbing this type of energy in the stratosphere. The reason why so much of this downgoing energy passes right through the atmosphere is that greenhouse gases cannot absorb it. But greenhouse gases can absorb infrared radiation. So if we turn our attention to the right side of this graph and the blue curve, when the Earth emits thermal energy, heat energy, which is essentially the leftovers of the solar radiation that it absorbed in the UV and visible parts of the spectrum, that thermal energy is slightly less energetic. It's found in the infrared spectrum. So the upgoing thermal radiation, the stuff that is emitted out of Earth's system, is infrared. And again, in this figure, the area under the blue curved line shows the total amount of infrared that is emitted. And the area that is shaded in blue shows how much actually makes it through the atmosphere and out into space. As you can see, unlike the downgoing solar radiation, in this case, a majority of the energy gets absorbed and only a minority, the part that's shaded in blue, gets transmitted and makes it out. And that's because greenhouse gases absorb that infrared energy. If we want to get more detailed on which greenhouse gases are absorbing which wavelengths of energy, here is a figure that shows just that. The bottom part of the figure shows a list of major greenhouse gases, and then the gray peaks on the graph show their capacity to absorb energy. As you can see, with the exception of water vapor, which absorbs energy across a wider range of the spectrum, these gases are mostly capable of absorbing energy in the infrared wavelength. You can also see the area on the left of the spectrum where they have virtually no capacity to absorb the wavelengths that are coming into the planet via solar radiation. So this is the essence of greenhouse gases heat trapping effect. And of course, not all gases in the atmosphere have this heat absorbing capacity. The four major naturally occurring gases in the Earth's atmosphere that are considered greenhouse gases are water vapor, carbon dioxide, methane, and ozone. And these gases are important to the functioning of Earth's systems. Greenhouse gases are not bad. Having some amount of them is good and important. Our current global average temperature is 15 degrees Celsius, which is about 59 degrees Fahrenheit. But without greenhouse gases and their heat trapping capability, it would be much less, much colder, minus 18 degrees Celsius or 0 degrees Fahrenheit on average. And while there has never been a point when Earth's atmosphere has had zero greenhouse gases, levels of these gases in the Earth's atmosphere has changed over time. And along with insulation and albedo, these greenhouse gas dynamics have also been a factor that mediates major changes in the Earth's climate over its geological history. A final note before we close out this section is that although these four gases are naturally occurring, human activities feeding into the production of these gases, especially carbon dioxide and methane. And we're also generating other non naturally occurring greenhouse gases, which is leading to an enhanced greenhouse effect and higher average temperatures across the globe. We'll talk more about those patterns later in this chapter.